So 7.1, integration by parts. This whole chapter in the Stewart book is one long sustained treatment of additional integration techniques beyond the first one that we learned, which was use substitution. And if you remember, use substitution was a way of undoing the chain rule. Okay? Well, here, integration by parts is a clever way of using the product rule in order to actually execute an integral that doesn't actually, up to this point, look like it's integrable. Okay? So here's what we're going to do. Okay? Let's go ahead and look at the product rule. And sometimes we do it in terms of, F and G. Today we're going to do it in terms of V and U. Okay? And this should be a recognizable version of the product rule. But what we really mean by that with the primes is that's U times dv dx, and that's V times du dx, isn't it? Well, let's go ahead and multiply through by dx. And if we do that, we get that. Now, let's go ahead and integrate both sides. And we wind up getting u dv and v du as independent integrals. And just by a little bit of rearranging of terms by simple subtraction, I'm going to get that. That is integration by parts, okay? And so what happens usually is we're given something like this. We're given something like x times cosine x dx. Now the problem here is that's obviously not u substitution. It's not u substitution because if I'm given, two expressions in an integrand, I need one to be able to be the derivative of at least part of the other, right? But since x and cosine x are two different classes of functions, I'm at a bit of a loss unless I have integration by parts. Because integration by parts allows me to basically deal with it in, you guessed it, parts. I want to designate part of this integrand as u and part of it as dv. Okay? Now, I'm going to go ahead and designate the way I know it, and I'm going to explain to you why in just a minute. Okay? We're going to go ahead and designate the u as x and the dv as cosine x dx. Well, I also need du and I need v in order to actually change the form of this integral. Okay? So I know that if I take the derivative of u is equal to x, I get du is equal to dx. That's easy enough. And if I anti-differentiate dv, I'm going to get sine x. Okay, well that gives me all four pieces that I need. And basically the first term is the product of these two. So x sine x minus, and then v du, sine x dx. So the first is a product of these two minus the integral of these two. Okay? Now, I've taken it from something that didn't look integrable to a term minus something that is very integrable. Okay? So basically that becomes x times sine x, and to integrate sine x, I'm going to get negative cosine. Well, that negative is going to cancel with that one, so I'm going to get plus cosine x plus c. That right there is my integral. Now, the question is, how did I know what to designate as u and what to designate as dv? What's wrong? What makes this integral a problem? Well, it's the fact that it's got both x and cosine x, okay? So I want to figure out one of them that I can get rid of. Well, cosine x is not going away, because the only thing that happens if you differentiate it or integrate it, either way, is that it just flip-flops back and forth between sine and cosine, and it's positive every 2, and then negative for 2, and then positive for 2, and then negative for 2. So basically it changes sign, and then flips back and forth between sine and cosine. So this is not going away. But if I designate the x as my u, it's a polynomial, and I know by the power rule when I differentiate that, it's going to go away. Okay? And that is how, when I wind up needing v du, since I've taken the derivative of u is equal to x down to du is equal to dx, I now have an x that has been gotten rid of, and I now have an integrand that is capable of actually being done. Okay? All right, well, let's go ahead and let's do another one. How about we do x times secant squared x dx. Now this one should be even more obvious than the last one, okay? It should be even more obvious because secant squared should look extremely familiar. Secant squared is a recognizable derivative of something. It is the derivative of tangent. And so if I designate my secant squared as my dv, I know that upon anti-differentiating it, I'm going to get tangent. So we'll go again with u is equal to x, and then dv is equal to secant squared x dx. I recognize the fact that du is equal to dx, and v is equal to tangent x. Well, you may not, quite have that memorized just yet. So basically we know that it's u times dv is equal to u times v minus v du. That is the formula, okay? So I've designated u and I've designated dv, okay? U, dv. Then I differentiated u and I anti-differentiated dv. Now, different teachers have different ways of actually setting this up and making it look different. I just like the sort of paralleling u and v and du and dv, so that's why I always start out with u and dv and then go that way, okay? However you want to set it up, however makes most sense to you. If your teacher does a little bit differently, that's just a matter of keeping track of stuff and notation and making things nice and clean and neat and making sense to our own minds. That's just incidental. So that's u times v minus v du. Well, tangent x, I don't know if you remember this, actually is one that we can integrate because it's basically a sine over cosine. It winds up being a natural log. If you want to do it by formula, it winds up being natural log of secant x plus c. But of course that negative out in front could change that argument of the logarithm back into cosine x. So it could be either one of those based upon the properties of logarithms. Remember, when you have a coefficient out in front of the log, you can pop it up as the exponent. And if I took that negative and popped it up as the exponent of secant x, it would reciprocalize secant x and turn it into cosine x. Okay. Okay. Well, that takes us a little ways along in terms of integration by parts. So basically, this is just a really neat way of creatively using the product rule in order to change the form of integrals such that they can actually be done. Okay. Well, let's go ahead and let's look at something like arcsine. Okay. Arcsine is something that we differentiate. Arcsine is certainly not something that we integrate. Okay? And you may be thinking to yourself, well, gosh, there aren't two pieces there. There aren't two pieces to that integrand, so how do I split it up into u and a dv? Well, you can just designate dv as dx. Okay? It doesn't have to be a really complicated dv. Dx actually is a recognizable derivative. Right? It is a recognizable derivative. So you can actually take dv. First of all, let's go ahead and put arcsine right here, because we aren't going to anti-differentiate arcsine. Okay, we're about ready to learn how, but it has to be done by parts. So, I mean, we can't pop it into a chart like this and anti-differentiate arcsine, but I do happen to know what the derivative of arcsine is. dv, if it's dx, when it becomes anti-differentiated, it just becomes x. Okay, and this becomes dx over the square root of 1 minus x squared. Well, that means that I have x, arcsine x, minus x over the square root of 1 minus x squared dx. Well, you know how to do this, okay? Or at least you should. That right there is just a simple u sub, okay? So all I would have to do in order to change the form of that is do a negative 2 out in front, put a negative 1/2 out in front, okay? And that changes this, arcsine x plus 1/2 into 1 minus x squared to the negative 1/2 times negative 2x dx. Now, I mean, you don't even have to really put that in. I mean, that winds up being u to the negative 1/2, and that winds up being du right there. So when I actually anti-differentiate that, it becomes 2u to the 1/2. 2u to the 1/2, the 2 will cancel out with the 1/2, u to the 1/2 plus c. Or if you want to turn it back into a radical, you can turn it back into a radical. I would really not care or bother to do so, but... And there you go. Okay? So all you're really doing is creatively using the product rule in a sort of a formulaic way in order to change a really messy integrand, which is oftentimes a combination of two different classes of functions, into something that can actually be executed. Okay, let's do one more, and then we'll call this first video to a close, and then we'll do another one. How about, oh gosh. How about x e to the x dx? Okay. And we'll just do some really easy ones on this first video, and then we'll get to more complicated ones in following videos. This one, obviously, is kind of the same variety as x times cosine x dx. And what I mean by that is this. If you differentiate or integrate cosine x, it changes form into sine x, negative cosine, negative sine, and stuff like that. But no matter how far you go in terms of differentiating or integrating, it never goes away. E to the x is the same way. E to the x, no matter how many times you differentiate it, is always going to be e to the x. E to the x, no matter how many times you anti-differentiate it, is always going to be e to the x. E to the x is not going to go away. And therefore, we want to designate u as x and dv as e to the x dx. Therefore, we have at least one piece of that integrand disappearing for us, which is, of course, crucial to making this into a form that can actually be done. And once I get to here, it's very obvious that it's x times e to the x minus e to the x plus c. Okay? We're going to hold off for just a little while in terms of doing definite integrals. I want to go ahead and get to a couple more complicated ones in terms of the indefinite integral. We'll also, in a future video, be doing ones called basically integration by parts tabular method. So that's something to look forward to. We'll probably do 3 videos on this, maybe 4, depending on how well number 2 and number 3 go. But we'll go ahead and pull this one to a close, and if you have any questions, as always, please do email me. I look forward to hearing from you.